Okay, so as Nadia said, I'm Victoria Interrante from the University of Minnesota, and I'm honored to be able to speak to you today about some of my lab's work involving embodiment, presence, and spatial perception in immersive architectural environments. So virtual reality has the potential to enable transformative advances in multiple application areas. And the one I'm going to be focusing on in this talk is architectural design, where virtual reality can allow architects and their clients to derive an experiential appreciation of a proposed building model before it's built. Now, when people experience VR using a head-mounted display, the common practice is to tie the position of the virtual camera to the position of the user's head, so that the images that are displayed behave as if they represent a view from the user's own two eyes. But for a variety of reasons, many applications don't attempt to represent the user's body in the virtual environment. And this can lead to a solitary, disembodied feeling, as if one is simply an observer of life rather than a participant in it. The reason that virtual reality has such potential to be an important tool in architectural design is that during the design process, the designer's imagination space is shaped in subtle but important ways by the tools that they have available to them for instantiating their design ideas. Now, my colleague, longtime colleague, Lee Anderson, who taught for almost 30 years in the Department of Architecture at the University of Minnesota, used to tell me that he could identify which software or which physical materials a student had used to come up with their design just from looking at the finished product. And this is because every medium will more easily support some things over others, and people tend to gravitate towards using the functionalities that are most straightforwardly available. So because our desktop architectural design software establishes a relationship between the architect and their creation, in which the model is external to themselves and small with respect to their own size, and where the actions needed to change the viewpoint are cumbersome and non-intuitive, the result is to privilege a focus on the external form of the building, how it looks as an object to be admired from the outside, over attending to the subjective experience that the internal spaces afford, how well the design works to create an environment that's going to be occupied and enjoyed. So immersive virtual reality has transformative potential for the design process because it allows designers and clients to experience the perspective building from a first-person perspective before it's built. This egocentric understanding is so important that builders will often construct full mock-ups of critical spaces before breaking ground on a new project in order to ensure that no design changes will need to be made once the construction is underway. So an example of this is when the company Mortensen Construction got a contract to build a new student dormitory on the University of Minnesota campus. And my architecture professor colleague told me that they physically built out one of the student apartments offsite at a cost of over $100,000 in order to be able to finalize their design decisions. And the logical question then is, why not use VR? And the answer to that is that that we need to make sure that the decisions, that the understanding that people derive from a building interior in VR, when they see it in VR, is the same as the spatial judgments that they would make in the real world. So for example, if client is trying to decide whether to choose the 8-foot ceilings or the 9-foot ceilings for the living room, we would want the ceilings to appear to be equivalently far from their eyes in VR as they would in the real world. And unfortunately, decades of research has shown that this is often not the case. So on the contrary, what researchers have found is that people tend to systematically underestimate egocentric distances in virtual environments. So egocentric distance is the distance between oneself and a target in the environment around oneself. And the amount of this underestimation was between 5% to 20% on average. And this is even using the modern lightweight head-mounted displays that provide a wide field of view. So if I'm 5 feet 7 inches tall and my eyeballs are 5 feet off the ground, and I'm looking up trying to judge the height of the ceiling in a virtual building, a 20% underestimation error would make a 9-foot ceiling feel more like an 8-foot ceiling, not exactly that bad, but 8.25 feet. And a 12 by 15-foot bedroom could feel more like a 10 by 12-foot space. So this is really a problem. And it's such a problem that builders, like I said, will build out full physical mock-ups of spaces in order to ensure that all of the design decisions are correct. So researchers have spent a lot of time and energy trying to solve the distance underestimation problem in VR. My own lab's earliest work with virtual humans began in 2008 when we used them to see whether people might feel more empowered to make accurate spatial judgments in VR if they could be induced to feel more present in the virtual environment by virtue of controlling a self-avatar embodiment that could offer familiar affordances for interaction with the virtual world. So our hypothesis was that distance underestimation might be a conservative response to the functional uncertainty implied by a disembodied view. So in a between subjects experiment, we asked 6 participants to make judgments of egocentric distance while they were embodied in the most realistic, fully tracked avatar that was available to us at the time. And we compared their performance to that of 6 additional participants who made the same judgments without an avatar embodiment. So in each case, the participants completed multiple trials in which a virtual tape mark would appear on the floor of a realistic virtual hallway in front of them. They would have to take visual aim at the tape mark, then close their eyes and physically walk in a real-world lab space until they felt they'd reached the target location. And after the participant had completed 20 trials in VR, we brought them to the real-world hallway, the same real-world hallway that we had modeled the virtual hallway after, and we asked them to make 10 more distance judgments, for which we used a physical blindfold and a real tape mark. So in all cases, the participants were never allowed to get any feedback about how close they come to the target, and they were never allowed to walk freely around in the virtual environment because we wanted to avoid introducing any potential confounds in the process. So this is what our setup looked like. I mean, it's sort of, you can see that it's dated, but this was work that was done in 2008. So the experiments were conducted in our VR lab, which was 30 feet long and in this direction, about 25 feet wide. We used the Vicon MX40 tracking system to animate the participant's self-avatar according to their own movements, and an N-Visor SX60 to present perspectively correct views of the virtual world to each one of their eyes. And each target tape mark was randomly generated at a distance that was between 8 to 20 feet in front of wherever the participant happened to be standing, so that they were never in any danger of walking into a wall. We always made sure that they were backed up against a wall before beginning each trial. This is the virtual avatar model that each of our participants was embodied in. We chose him because he was generically addressed in an attire that seemed appropriate to the student population of our university, and only the lower half of the body is generally visible from the participant's perspective, so he could work just as well for our female participants as our male participants. When we fit this avatar model to each of our participants, we made sure to scale not only the height of the avatar to match the participant's height, but also the length of the avatar's feet to match the length of the participant's own feet. So this slide shows a photograph of the real-world hallway that served as the basis for our virtual environments model. This is where the participants made distance judgments while not wearing the headset, and that was to provide us with a per-person basis for comparison with the distance judgments they made in VR. And this is an important thing to do because some people will just naturally tend to be cautious when you tell them to close their eyes and walk. And out of caution, they might take shorter steps and therefore think that they traveled farther than they actually had, stopping sooner than they would have if their eyes had been open. Other people might be much bolder. And if we have real world data for each participant, that allows us to control for those individual variations when we look at how people are behaving in the virtual environment. So this is a screen capture that shows what our virtual model looked like. And you can tell it's a computer generated image because of the aliasing along the edges of the doors. But when you were immersed in it, it actually felt compellingly realistic. So this model was created in 3D by my architecture colleague, Lee Anderson, in using the SketchUp software. And he textured the geometric model with photographs of the real space in order to be able to accurately capture all of the nuances of the physical lighting on the walls and the texture of the doors and so on. And this image shows what the embodied participants saw when they looked down. So we wanted to ensure that everybody was exposed to their embodiment at the start of each trial, but we didn't want to explicitly draw people's attention to the fact that they were embodied in case that, had an effect of some kind. So what we did is we told people that we were going to generate a tape mark and that they should line up their toes with the tape mark. Now, the participants who were not embodied didn't get a tape mark. They just looked ahead and saw a target that they closed their eyes and walked to. The participants who were embodied lined up their feet with this tape mark, then looked for the farther tape mark, closed their eyes and walked to where they thought the farther tape mark was. And so this is what we found. Now, for the participants who were not embodied in an avatar, they walked significantly less far in the virtual world than they did in the real world. So each point on this chart represents the average relative error across all of the trials completed by a single participant, comprising 20 walks in VR and 10 walks in the real world. And the x-coordinate of each point is defined by the participant's average relative error in the real world. And we can see that while there's some variation, they're more or less centered around 0. So some people are walking a little bit farther than they should. Some people are walking a little bit less than they should, but they're pretty much centered around 0. So the y-coordinate of each point is defined by the participant's average relative error in VR. So points that fall anywhere along the diagonal line would represent behavior that's similar in VR as in the real world. So maybe somebody overestimates by 25% in the real world, they overestimate by 25% in VR, they would end up at the same, at a point along this line. All of the points that fall below the diagonal line represent situations in which participants walked shorter in VR than in the real world. So what you can see here is that we've got a few people who are represented by the white and gray points, had performance that was not statistically significantly different between the real and virtual environments. And this is really common. We find this in almost all of our studies. There's always just, some people who are just spot on. But when we look at the participants as a group, the majority of participants underestimated the distances in VR, and they underestimated by pretty substantial amounts. If you look at these points, it corresponds to 30% to 40% underestimation. So 40% underestimation is you show people a target that's 10 feet away and they only walk 6 feet. That's pretty significant. So this slide shows the results for the participants who were embodied in the avatar that I showed you earlier, and they did consistently better. So distances are still being underestimated, overall. I mean, we've got the few that are spot on, and we've got the most that are under the line. But the underestimation is less severe when the avatar embodiment wasn't provided. So from this experiment, we were able to conclude that providing people with a with a size-matched self-embodiment in VR, we could lead them to adopt a more accurate interpretation of the spatial extents of the virtual environment that they were immersed in. However, the improvement that we got from the avatar embodiment wasn't quite enough to definitively solve the distance underestimation problem. So then we had to make a decision about what to do next. So the next essential question in our research was, could we potentially do better in facilitating accurate spatial perception in VR. If we could somehow provide people with a higher quality avatar embodiment. And if so, then it would be worthwhile to invest in a research endeavor towards higher quality self-avatar implementations. The problem is, we were already doing the best we could in terms of providing people with the best avatar that we could possibly give them. So we had no way to test that question directly. Instead, what we chose to do is to see what would happen if we were to compromise the avatar quality by reducing either the geometric fidelity or the motion fidelity. And the practical advantage of that approach is that we could also then determine if we might be able to get away with using less resources. If a lower quality avatar was just as good, then we might not have to go to so much trouble. So what we did is we conducted another between subjects experiment. We recruited 28 additional participants, 10 of whom experienced a geometrically faithful but motion compromised avatar. So the avatar was non-articulated, and it was anchored to the position of their torso. And 10 of the participants experienced a faithfully animated but geometrically sparse avatar, where all of the motion tracking markers were represented as small spheres, and so they could see. You're probably familiar with these point light displays. So it was sort of inspired by that, where you could see the spheres moving as you moved, but there was really no geometry there. And then the other participants were divided into the other conditions to fill out all of the data points we needed. So this is what the stiff avatar looked like. I mean, I know he looks really awkward, but fortunately there were no mirrors in our environment, and participants were never able to see themselves from this vantage point that we're using right here. What they would see though is that when they had the virtual tape mark and they moved their feet up to alignment with the virtual tape mark, the avatar would just sort of gradually slide forward as their torso moved forward, and you wouldn't see the movement of the feet. This is what the dot avatar looked like. So again, the participants never actually saw themselves from this vantage point. What they saw looked more like this. So what did we find? This is what the data looks like in the case of the stiff avatar. You can see again in the real world, people are centered, pretty much around zero. I mean, some people, like this person right here, is walking, underestimating by about 25% in the real world, but they're also underestimating by about a little bit over 25% in the virtual world. So this represents just sort of a cautious individual. On the other hand, you've got individuals like this one who are pretty much spot on in the real world and underestimating in VR by more than 50%. So we show them a tape mark 16 feet away, they close their eyes and they walk 8 feet in VR. In the real world, we show them 15 feet away, they close their eyes and they walk the whole 15 feet. So this is sort of a mixed bag here. And with the dot avatar, we saw something sort of similar, intermediate between the two other cases. So with this chart shows a summary of the data from all 4 conditions. And what you can see is that people did best with a full avatar, worst with no avatar, and performance was intermediate for each of the compromised avatar representations. So these results suggested to us that it would in fact be worthwhile to devote some effort to trying to research effort into trying to improve the quality of the self-avatar if our goal was to enable more accurate spatial judgments in virtual architectural environments. But before I launch into a description of our research efforts in that direction, I want to do a little bit of a side detour into another architectural related use of avatars, and that's on the topic of virtual human entourage elements. So entourage elements are little figures of people that architects will add to their drawings to provide a sense of scale and to bring the drawings to life. So here's a a photograph from a website where the architect is explaining to people, what the stages are in putting together an architectural design, and stage 2 is add entourage. So stage 1, which I'm not showing, shows the same building but without all the little people around. So without the little people, it's hard to tell how big how tall the building is, etc. But with little people, you get a better sense of the scale. And so we asked ourselves, is it possible perhaps that instead of going through all of the trouble of putting people into a tracking suit and tracking all of their motions, maybe we could just add these virtual human entourage elements to our virtual building models and help to enhance spatial perception accuracy that way. So specifically, we conducted an experiment to determine whether the presence versus absence of a static or dynamic photorealistic model of a known real person would lead to reduction in distance underestimation errors. So the reason that we used a known real person is that people come in all different sizes and shapes. And I was a little bit skeptical of the idea that just putting any random person into the virtual environment would make a difference. But at any rate, I'll get to that a little bit later on in the talk. So we recruited 18 participants, and they made egocentric distance judgments in 3 different virtual interiors under 3 different conditions of virtual human entourage. So there was no virtual human, a static virtual human, or a dynamic virtual human. And so we matched, so each virtual human appeared in a different virtual environment, and we scrambled the correspondence of virtual human to environment between participants so that at the end of the experiment, every virtual human had been seen in every different environment multiple times. And the virtual human model that we used was a scanned 3D model of the young woman who was running the experiment, and the participants would meet her before entering the virtual environment. So what you see on the next slide is this is the real Carla, and this is the virtual Carla. So we scanned her using a handheld scanner, and you can see that it's, the likeness is really good, but at the same time, there are these sort of annoying artifacts, and the shoes had to be added on as a post process, because we had a hard time. The depth sensor had a hard time resolving the shoes from the floor. But at any rate, this is what we had. And here you can see the 3 different virtual environments that Carla built to house her virtual self, and people would again open their eyes, they would see a tape mark, they would see the virtual Carla, they would close their eyes, walk to where they thought the tape mark was. And so sometimes the virtual Carla would be stationary, or stationary with an idle motion. And sometimes what would happen is the virtual Carla would walk down, appear from behind the participant, walk down the hallway, and exit through one of the doors, and then the participant would make their distance judgment. And so what we found is that our participants consistently underestimated distances in the virtual environment by a lot. So this experiment was done using an HTC Vive, which is a modern headset, but you can see that the artistic quality is really low. So whatever it was, people were really underestimating distances. And furthermore, so if we showed them 8 feet, they would walk 6 feet. 10 feet, they would walk about 8 feet. So it's pretty much 16 feet, they would walk 12 feet. So it's a pretty much consistent 25% distance underestimation for all 3 of the different avatar conditions. So we didn't see any added, there's no evidence here of any added benefit of the presence of the virtual Carla model in terms of the accuracy of people's distance judgments. And that was And that was a little bit disappointing. And one of the things that you always do when you get a null result is to do kind of a sanity check. And the sanity check here is that as people were shown distances, that people walked farther as the distances got farther. So if it was just noise or something, then we wouldn't see this pattern. But we do see a rather consistent pattern of how far people walked versus how far the tape mark was from them. It's just that the avatar didn't make any difference. And so that was a little bit disappointing, but we decided to conduct a follow-up experiment using a more realistically rendered virtual hallway environment. And in this follow-up experiment, we also wanted to look at how the size of the virtual human model might affect people's distance judgments. So what we did is next slide. Okay, so we recruited 36 participants, 12 in each of 3 conditions, and we asked them to make egocentric distance judgments in the presence of a virtual human that was either its actual size or 20% smaller or 20% larger. And then afterwards, they did distance judgments in the matched real world environment. And this slide shows what that situation looks like. So we have a new experimenter. This is Sahar. And this is the actual size Sahar, 160 centimeters tall. And this is the shorter Sahar, 128 centimeters, and the taller Sahar. And then we would have a tape mark on the floor. People would close their eyes and walk to where the tape mark was. And the virtual Sahar model didn't really do anything except just stand there. And our hypothesis was that people might have, if the virtual human was going to have a positive effect on improving the accuracy of people's spatial judgments, that people would be more accurate in this case than in these 2 cases. And in particular, when the virtual Sahar model was bigger, they might underestimate distances more than when the virtual Sahar model was smaller. So what was really interesting about the results that we found is that, again, people underestimated distances in all 3 cases. So what you can see here is each of these circles corresponds to a data point from an individual participant. And the gray points, they're really hard to see, are from the trials that were done in the real world. And the colored points are from the trials that were done in the virtual world. And I've got these dotted lines, which you can barely see, that represent the sort of best linear fit to the data. And so here we can see that in the real world, people were, pretty much, and the black line, of course, is ground truth. So in the real world, people were pretty spot on. But in the VR, people were underestimating. This is the small avatar condition. The large avatar condition, we see this group of participants was slightly underestimating in the real world and underestimating a lot in VR. And this group was actually underestimating, by a not insignificant amount in the real world. That just happens, by random. You get people who you get more people who tend to be shorter walkers. And then this is how they walked in VR. So it's clear again that people are underestimating distances across all 3 of the avatar conditions. We ran statistical analysis, and that showed a slightly greater amount of underestimation in the large avatar condition relative to the small avatar condition, and slightly more similar amounts of underestimation between the real and virtual environments in the right-sized avatar condition than in the conditions with the mismatched avatars. But there's really no consistent pattern of behavior that would suggest that people might be scaling their responses according to the avatar size. Because if that was the case, then we would have expected to see the least amount of underestimation in the small avatar case, and we do not. And then this slide just says what I already told you. Okay, so now let me tell you a little bit about the efforts that my lab has undertaken towards achieving higher quality self-avatars for use in VR. So there are 2 fundamental approaches that we can take to self-avatar representation. We can take a person, obtain a 3D scan of them, and then track their movements and animate the 3D character according to their movements. Or we could use head-worn cameras to enable people to see their own body in VR, and their own body or the bodies of other people. So each approach has its strengths and its weaknesses, and neither of the technologies are really fully mature yet. When you're modeling and animating 3D characters, you still have to get the facial movements, and that can be a little bit tricky. When you're using cameras, background subtraction is always the problem, and latency and so on. And so we sort of had to make, there was a fork in the road. We had to make a decision, which path are we going to go down? And so we tried to design an experiment that would help us to answer that question. So here's some examples of the work that we did with video self-avatar. So this is the PhD research of Lauren Fiore. You can see it was done a while back, because we're still using the Envisor SX60, and it's got an Intel Creative Sense 3D camera attached to the front. So we've got a RGB camera and a depth camera, and these cameras gather, these cameras get a view of the real world, and then that view of the real world is reprojected from the point of view of the two eyes of the participant. So when you look down, this is actually my own left hand in the context of the virtual architectural environment. And you can see that it's a virtual environment because we made a mistake with the location of the shadow here. But at any rate, you can see that the virtual world will include the avatar, and the avatar can also include the virtual world, because we have 3D information about the location of a person's body. So this was, really, compellingly realistic. The problem is that the camera communication latency, between, as we pull the data out of the real sense and we send it to the computer, and then we process this and send it back to the headset, we would get about 120 milliseconds of delay, and that is just fatal. I mean, I could put on the headset and I could last in there for about 3 minutes, and then I would have to take it off because it was just too laggy. And then we also have the problem of limited depth sensor range. I mean, these cameras, they keep getting better and better, but still there's either they would show, either they would fail to capture information that was close, or they would fail to capture information that was far. And we really wanted to have both far and close, so people could see themselves and other people. And then, of course, the background subtraction is a extremely challenging problem. And you also have to deal with sensor noise and missing data, and also inconsistencies between the lighting on the real object from the physical environment, and the lighting that is active in the virtual world for the synthesized VR content. And so this slide shows some of our results with the higher quality 3D self-avatar. So this is, again, my student Sahar. She got a model of herself scanned, using a more professional outfit, and here she's wearing the headset. And so with these scanned avatars, the main advantage is that the models are modifiable. So if you want to say, change the skin tone or something, it's really easy to do that. The problem with the video self-avatars is, what you see is what you get. Challenges with the 3D scanned avatars is that everything that you want to move, you have to track, and that's particularly difficult for the fingers and the face. And then, of course, close animation is non-trivial. So both of these. So we had to kind of decide, which path are we going to go down? Are we going to go down the path of trying to solve the background subtraction problem? We're going to go down the path of trying to, figure out how to, more faithfully track fingers and faces. And so in order to make that decision, we conducted an experiment which used a visual haptic cue conflict paradigm in order to compare the strength of the confidence that that was evoked by the video-based versus the scanned self-avatar representation. So this line of inquiry was inspired by a seminal paper by Ernst and Banks, published in 2002, where they'd shown that when you force people to integrate conflicting information from two different sensory modalities, in particular vision and touch, what people do is they'll weight each of these cues according to their sense of the cue's reliability or trustworthiness. And so we sought to use this principle as an objective to objectively measure the implicit trustworthiness of each of our avatar representation types. So for example, if the video-based approach is somehow inherently is going to be, result in an inherently stronger sense of confidence in the avatar representation, then we would expect people to weight the information that they get from the visual modality more heavily in the video avatar case, for example. Okay, so here's this slide shows what the experiment looked like. We had 12 participants, and we asked them to make to tell us the size of a block that they saw and touched at the same time. And so and this was across two different conditions of virtual self-representation. So so in half of the trials, they saw a scanned avatar, and in half of the trials, they saw the video see-through avatar. So in this case, you can tell that this is the scanned avatar. So what we did is we brought people into the lab. They presented us with their hands. We scanned each one of their hands. And then each of these hands was a rigid body model, which we tracked using these Vicon trackers. And in this case, we're using now we're using the Oculus Rift with an Intel RealSense camera on the front of it. It's the same idea. It's seeing it's capturing 3D, a 3D height map essentially of everything in front of it. And because of the black background, we're only actually seeing the participants' hands because the other is IR absorbent, and so it shows up as empty in the virtual environment. Yeah, except of course, we had to do a lot of tricky work to make this work. But at any rate, this is what people saw in the two different conditions. And so how the way that this experiment worked is that we trained the heck out of people in the real world first. So we had these 7 different block sizes, and people had to go through an exhaustive training procedure where we picked a subset of these blocks. We would show them the block, we would tell them its size, then we would take it away. And then we would show them a different block. We would tell them its size. We would take it away. And then we would show them the block again, and they would have to tell us its size. And if they made any mistakes, they'd have to go back to the beginning. And after we'd done that with a subset of the blocks, we would show them blocks that they hadn't seen, where we hadn't told them the size yet. So we might show them this one, say, this is 18 inches, this is 12 inches, this is 10 inches, whatever. And then once they were good at reporting back the blocks that we told them the size, we would show them a block where we hadn't told them the size, and we would say, how long is this block? And if they made a mistake, they would have to go back to the beginning and repeat the whole thing. So they did this with vision, and they also did it with touch. So with touch, what we would do is put a blindfold on them. They would touch, they would move their hands. I don't know, I can't see my camera. I don't know if you can see my hands. So they would move their hands until their hands were just touching the sides of the blocks. And then we would tell them, this is an 18, this is a 12, this is a 5, or a 4, and so on. And so when people had gotten through the training process, they were really spot on at this task in the real world. And so then we put on the headset, and we put them in VR. But when we put them in VR, what we did is we introduced a visual haptic cue conflict. So in this case, we're showing you the the scanned avatar model. And this is my PhD student, Shihang Zhang, whose work this is. And you can see here, they're touching a block that's 18 inches in the real world, and they're seeing themselves touch a block that's maybe 4 inches in the virtual world. And of course, we can do it the other way around. And then what we ask people to do is to give us one number that best represents their sense of the size of the block. And so if they were, just move on to the next slide. So, so our hypothesis was that people would tend to answer more based on what they saw than what they felt, so that visual dominance would be stronger in the conditions where, well, I guess I should go back a little bit and tell you what's going on here. So we also had a third of the trials were in a condition where we didn't show the block at all, but we only showed people's hands, because we thought, people might be, it's possible that people would just be ignoring the hands and only basing their judgment on the block itself. And so we wanted to have this as a control condition where the block wasn't visible and people could only use their hands. So they saw their hand, they saw how far apart their hands were, and they felt how far apart the block was, and they had to give an answer about the block size. So our hypothesis is that there would be greater visual dominance in both of the conditions that had the avatar and the visible block, but that if people felt a greater innate level of trust in one of the virtual body representations over the other, then we would have expected to see greater visual dominance in that condition. So, so what we found, though, in the end, is that participants really gave equivalent weight to the visual stimulus in both of the avatar conditions. And as might be expected, the visual dominance was weakened when the block wasn't visible. So we knew that our technique was working. It just wasn't giving us, it just wasn't differentiating the two different avatar types. And in addition, we gave people surveys about agency, ownership, visual realism, experiential realism, and the results were really not statistically significantly different between the two avatar conditions. So what this suggested to us is that really there's no inherent fundamental potential advantage to one of these approaches over the other, and that's a good thing to know. So now I'm coming to the last of the pieces of work that I'm going to talk to you about, and this is some PhD research by my student Sahar. And the goal of our research in this area was to support architects in immersive architectural design review. So in a design review, what happens is multiple stakeholders will meet together to discuss their design ideas. And we wanted to allow each of the stakeholders to be able to put on the headset, see themselves in the virtual model that they were discussing about, and then to see each other while they were discussing about their virtual model. And so our architecture colleagues told us that the minimal requirements they needed for the embodiments was to be able to know the position and orientation of each of the participants' head and hands. And they were, sort of, just fine to go with that. So just, a floating HMD and a floating pair of controllers, and we'll be fine. But, our research, we thought we could probably do better by filling in a full avatar. And we wanted to compare, again, the 3D scanned avatar model with a video see-through technology. So we asked 36 participants to engage in structured interactions with a confederate who was embodied in a similar manner to them under 3 different conditions of avatar embodiment. So the first condition, we call this no avatar. The tracked locations, the tracked 6 degree of freedom poses of the headset and the controllers were available. So the participant looked down and they saw 2 floating controllers when they put their hands out in front of them, and they saw Sahar as a floating headset. In condition number 2, this is the scanned model of Sahar, which we rigged using Mixamo and then animated using inverse kinematics. And so this is the 3D scanned approach. And this is the video see-through approach. So we still haven't solved the background subtraction problem. So we just punted and used a green screen. So here's real Sahara standing in front of a green screen, and the green screen allowed us to show the real Sahara in the context of the virtual architectural environment. So this space is actually the courtyard of our architecture building on our campus. And so the dependent measures we had after every block. So there were 3 different, I didn't tell you about the tasks. So we had 3 different tasks. One was a conversation cards game where it was just designed to encourage discussion between the participant and the confederate, who was always Sahar. For every participant, just talk to Sahar. So we had conversation cards game. We had a survival items game where the participant and Sahar would negotiate about which 5 items they wanted to use to save themselves from a zombie apocalypse or something like that. And Sahara's goal was to try to engage the participant in negotiations about, so she would disagree with one of their suggestions, and that would spark conversation. And the third game was a charades game. So the association of games to avatar representations was again scrambled between the participants. So some people would see this avatar with the charades game, some people would see that avatar with the charades game, and so on. And we used 3 different games because we didn't want people to get we didn't want holdover effects between the different conditions. So after every block, we gave people surveys about how they qualitatively rated their level of social presence with the avatar, their level of interpersonal trust with the avatar, their satisfaction with their communication with the avatar, and their attention to behavioral cues. So like how much attention did they pay to the avatar's body motion or facial animation or so on. And we also collected quantitative measures of the time that they spent trying to engage in mutual gaze with the experimenter and the number of unique words spoken. And then at the end of the experiment, they had to rank the 3 representation types in preference order. So what we found is that the ratings of co-presence were significantly higher in both of the model-based and video-based avatar conditions than in the headset and controllers only condition. And the exit survey also showed a strong overall preference for the video-based avatar representation. The video-based avatar representation was also associated with high ratings of interpersonal trust and more prolonged attempts at mutual gaze than the other 2 representation types. And so, we found this, really interesting. This was the first time that we'd really seen a difference between the scanned avatar and the video-based avatar. So one thing that I have to remind you is that our scanned avatar did not have facial animation. In fact, if I go back to this slide, you can see that the face of the avatar was pretty much obscured by the headset. And this is how it has to be. Everybody's wearing a headset, so the headsets are blocking their faces. There's future work that could be done to try to remove the headset and show the face, but we didn't to keep things equivalent across the 3 conditions. All 3 avatar representations were wearing a headset. So this one doesn't show the depth camera that was used to get the video. Only the participant. We only had one headset with cameras, and that was the one that was worn by the participant. So participants saw Sahara looking like this, and what Sahara saw was just, I think she just saw this in all 3 cases. But at any rate, it was interesting that the participants preferred the video representation for interpersonal trust and some of the overall negotiation. And I think it's because even if you can't see a person's face, when you see the video representation of them, you know that you're talking to them. And so when you have to do some sorts of delicate negotiations, it may be a little bit easier with this type than with that type. And generally people were less happy with the no avatar condition. So for concluding remarks, if I want to sort of encapsulate the points that I want you to walk away from this talk with, is that self-avatars can help to support more accurate spatial perception in virtual reality, and higher fidelity avatars seem to help more than avatars that are deficient in their appearance or their movement. So, so investing in the highest quality possible avatar does seem to be wise if the goal is to support accurate spatial perception. And so then we ask, why is accurate spatial perception better supported by these cue-rich self-avatars? And it's a little bit difficult to pin down, but my sense is that the benefits are really less likely to stem from greater visual realism than from the greater experiential realism that the realistic avatar will afford. So you just start acting in VR the more closely to the way you act in the real world. Your affordances for interaction with a virtual environment are more similar to the affordances for interaction with the real world, and that then leads to evokes behaviors that are more similar in VR and the real world. Also, what we found is that the presence versus absence of virtual human entourage elements doesn't seem to significantly affect egocentric distance judgments in virtual architectural environments. This is a little bit disappointing, and and it's fair to ask, why do self-avatars help but virtual humans don't? And I think the reason is that an avatar embodiment really does much more than serve as a referent for size. When you're embodied in a virtual environment, this likely increases your confidence in your confidence for interaction in the virtual environment, that it will be similar to, that it will provide similar affordances for interaction as in the real world. And finally, we found that video-based avatars can better support some aspects, not all aspects, but some aspects of social engagement more effectively than realistic scanned avatars that lack facial animation. And both types of avatars outperform rudimentary or symbolic avatars in multiple respects. And so altogether, these results underscore the importance of continuing to strive for increased representational fidelity in avatar embodiments. But at the same time, I don't want to say that high visual realism necessarily needs to be the goal. What we're really shooting for is high experiential realism, and high visual realism, may be one way to achieve that, and there may be other ways to get there that don't involve high visual realism. And I have a whole nother area of research that's looking at non-photorealistic virtual environments and how people behave in those types of environments. So I would like to, on this slide, acknowledge all of the people whose work went into this slide presentation. My colleague Lee Anderson, PhD student Brian Reese, PhD student Lane Phillips, PhD student Lauren Fiore, Shihang Dang, and Sahar Asiri, and undergraduate student Carla Pariso and Michael Kading, and of course the multiple grants from the National Science Foundation and the Linda and Ted Johnson Digital Design Consortium. So I think we have a few minutes for questions. Nadia, I can't hear you.
Thank you for the interesting talk. And I think this research could be very useful today for architects, because more and more, when you like to buy an apartment, you are offered 3D glasses, to visit. And I was not myself very aware that this perception, spatial perception, could go until 20% wrong. So what is the future of that? Because it seems that still the results are not completely satisfactory. So how do you see the future? Because what I found very interesting in this research is it's very much used. As I said, today you go to buy an apartment and very often you are offered, this kind of 3D visit of a virtual apartment. So if what you see is 20% wrong in terms of what you will have, I mean, this kind of research is very important because you engage yourself in buying something. So how do you see the future? What will be the next step in your research? We have seen over 2010 until now with the self-avatars via scanning, where it could be eventually better. But what is next?
Yeah, that's a really good question. I mean, I think I have a lot of confidence that as the technology improves, the accuracy of spatial perception in VR will just increase. And so I also think that there are so many advantages that you can get from virtually visiting a building, even that that don't necessarily have to do with spatial judgments. You're experiencing the windows and the light and the ambience of the place, and maybe it's not so important to say, like, if you're choosing which apartment you want, it might not be as important to know that the ceilings are 9 feet versus 8 feet. I mean, you could potentially feel like you don't want an apartment because it's too small when it's actually just fine in terms of size. I think you're really right about that. And I don't really see a good solution to that problem until we can. I mean, I think embodying people will definitely helps, but the embodiment comes at a price in terms of the encumbrance, and I don't think we really have a good solution to that yet. So as far as my lab, we're still working on trying to improve the qualities of the quality of the avatar representations. We're looking at I don't know, how to do everything that we've already done, just a little bit better. And it's a rather long and tedious path, but we keep plugging away at it.
Any other question? Any question from the audience? Yes, you can use the chat or yeah. So as long as the waiting for question, I have another question. You mentioned you have worked on psychiatry. So what were the parameters you studied? Because here it's mostly spatial perception. Also, when you use the blocks, was really this with embodiment or no self-embodiment, but or with the hands. But in psychiatry, what did you study? In fact, I guess it's not the spatial, or is it?
Yeah, so I had actually two different collaborations with psychiatrists. So one of them, we were looking at executive function and using virtual reality to be able to gather more ecologically valid measures of people's ability to get around in the world. So for example, if you have an elderly parent who is in sort of like has mild cognitive impairment, you could take them to the office and they could be given a battery of tests, but drawing a line from from those tests to whether or not they can independently go to the supermarket and come home with the things that they plan to come home with, for example, are sort of two separate questions. And so what we were doing there is we built out a virtual supermarket, and we had people performing tasks that required the use of executive functions as an adjunct to the traditional pen and paper tests that the psychologists were we're using. And that was work that was done a few years ago. But right now I'm working with a different set of psychiatrists who are interested in helping children to reduce their fear of getting brain scans. And so we're creating a 3D virtual environment of the magnetic resonance machine and building, so that the therapist can walk through with the participant what the procedure will be like to try to reduce their anxiety.
So
Yeah,
any
so
further questions? Are we limited by time?
I have just one small
Yes.
question. So you mentioned about the model-based avatar and video-based avatar. So when you do the video-based avatar, which is the most preferred by the users, it seems, how do you use the video-based? Do you use the green background, or you use some kind of AI to get the human silhouette, or how do you do that?
That's a really, really, really good question. So we tried for many years to develop software that could robustly accomplish the background subtraction. And we just weren't able to get it to work well enough. And so when we ran this experiment, we just covered the entire room in green screen fabric. We bought yards and yards and yards of green fabric, and the whole environment was just like a green room. And then we put the participant and Sahar would stand. I mean, it wasn't the entire lab, it was just a portion of the lab, but that whole portion was covered with the green fabric. And so when participants looked down, we used the green to do the background subtraction, so they could see their own hands, and then they could see Sahar, and then they were both all of the empty pixels were filled in with the view of the virtual world. So the impression was as if they and Sahar were both standing in a virtual building model.
So for the
we cheated, basically.
model-based, do you use the 3D scanner, or do you use just some kind of a photo-based modeling method?
Yeah, so in our first experiment with Carla, we used what's it called, a structure sensor that you attach to the back of an iPad, and you hold it and scan the model, and then it kind of stitches it together. But we found that it's really difficult to get high quality results with those types of scanners. And we for another experiment, which I guess for the experiment where we had the scanned hands, where we were doing the block size, we borrowed a high quality scanner from the liberal arts college, where they were using it for geological artifacts or something like that. And so we got a pretty nice model, but still it was difficult because participants had to hold their hand really still, and then we had to move the camera all the way around their hands. And if they moved just a little bit, then things would not work. We got the model of Sahar by actually going to a professional company based at the Mall of America in Minnesota, where she stood in a photo booth, and they took a number of pictures simultaneously, and then stitched them together to give her that model. And it looks really nice from a distance. The problem is that the fingers are not well articulated. So I think in the mesh model, they're all just sort of like stuck to each other. And so a lot of post-processing work needs to be done to split the fingers apart. And then of course, if we want the fingers to move, we need to track them, and that also comes with its own burden. So there's still a lot to be done to get either of these approaches to work in a robust manner.
Yeah, because if you have the 3D model of a body, you need to have a separate animation system, so that if the person, the user is moving around, you have to get the motion of the person to reflect with the model, the virtual model of the person. So do you do the animation as well, or you are just using the static model?
Well, no, in the very last experiment, we used inverse kinematics. So I think it was a final IK package in Unity where they had the headset was 1 point. They held controllers in each hand, so there were 2 points. Then they had a Vive tracker attached to their torso on a belt, and then they had a Vive tracker attached to each foot. So we had 5 points. And from those 5 points, we were able to use the final IK package to infer the pose of the avatar. And it works pretty well. It's not perfect, but it's not as bad as as the artifacts that we used to get with the Vicon, where somebody's arm would be like upside down. That's how we don't get that anymore. Thankfully, but it does mean that people have to put these things on. And what my colleague Lee Anderson told me was that people really don't want to be bothered, and so especially high profile clients, it's hard to even get them to put on the headset because they don't want to mess up their hair. So it's there are all these other considerations that you have to keep in mind, or that we all have to keep in mind as well when we're developing this technology.
Okay, thank you very much.
Well, thank you so much for giving me this opportunity to talk with you, and I really appreciate it.